Hello, everybody, and welcome back. Today, we're going to talk about the NBA's billion-dollar load management strategy and why it's a spectacular failure. Not only are injuries not decreasing, you could argue that they're actually increasing. Sports science is obsessively focused on the wrong half of the injury equation and leaving athletes fundamentally underprepared and chronically exposed. So in recent events, NBA Finals just ended, and Game 7, you hate to see it, but Tyrese Halliburton went down with a ruptured Achilles.
Okay.
I remember watching the game and hearing the announcers talk about it kind of before, talking about he had a leg injury. I wasn't sure what it was, but they said he had a calf strain. I was like, oh, God, I hope he doesn't have a blown Achilles. And sure enough, that first quarter,
Yeah.
he went down and he knew it. It was heartbreaking.
Yeah, you
Because
never want the game to be like altered by an injury like that.
I mean, yeah, and it's not the first actually, or the second blown Achilles in the playoffs. We both had Jason Tatum earlier, a good St. Louis boy,
Hmm.
and then also Damian Lillard, and then
Right.
also recently noteworthy players. We had Aaron Rodgers, blown Achilles, Kirk Cousins, and then a little bit differently. Uh, Different sport in Major League Baseball, we kind of see this like UCL injury.
Hmm.
We had Corbin Burns most recently, and Spencer Strider as well.
Yeah, it's funny because is this the most Achilles tears we've seen in the NBA?
I think in for sure one season, yes,
Yeah, so it seems like
especially in a finite period,
yeah,
kind of in the playoffs when kind of uh, the season's coming to end, so they're experiencing more playing time, and you could basically say it's like an overuse injury.
yeah, and I think that that's what the whole load management or load management breaks are trying to kind of tap into as far as like giving the players rest, but it's not really addressing the problem, is it?
Yeah. So, as far as injury is concerned, yes, today we're going to talk a little bit more about uh, injury prevention and
Right.
how to kind of best fight that. And we're going to take a look at kind of the NBA and kind of why you see uh, their strategy is kind of just not working and it's not really tackling and focusing on the right things.
Yeah, I mean the whole workload, chronic workload, acute workload, load management, I think is the hot topic. So we've got all these sports scientists that like every team has their data guy, right? And they're looking at GPS data. They're looking at how many minutes are being played, all of these types of things, and then they're putting this all into this like total load accumulation, right? And then they know whenever a particular load becomes exceeded, the injury risk starts to elevate. So we see people like high leverage players, the people that everyone wants to see, they're now taking breaks, right? To be able to try to mitigate some of these potential injuries. But what we're finding is it hasn't really made that much of a difference, right?
Yeah, I think you can argue. I think that there's too many games being played, especially basketball and baseball as well. Baseball has always been like an ongoing issue,
Yeah, I mean,
but it still doesn't really. It's still not really solving the problem because uh, all if we were to break down injury and put it in like a simple kind of formula, it would
right,
be whenever the load exceeds the capacity of the tissue is going to injure.
correct. Yeah, so that's simple math equation, but it holds true for every single injury. That tissue doesn't have the demand or doesn't have the capacity to meet the demands.
Yeah, and so uh, these professional teams are kind of they're trying to tackle it just from the load. So they're trying to decrease the load, which will, I guess you could argue, then therefore decrease, the risk of injury.
Hmm.
But the better course of action is just building up the capacity of the tissue to deal with what you're asking it to do.
Correct. And I think that that's also a bit of a failure on the training side because they're not truly addressing all the trainable qualities. You know, the nervous system and muscle gets all the attention, but as we'll talk about here, like the connective tissue, the architecture of how the connective tissue is designed isn't really being addressed.
Yeah, because when an injury happens, it happens at the
Connective tissue level. So we know across the board, doesn't matter what sport, 70+% of all athletic injuries happens to the connective tissue. So any type of like wear and tear, like rotator cuff strain, whatever it may be, is going to be more connective tissue based rather than muscle based.
yeah. So how do we go about uh, maybe shifting our focus from trying to manage loads, manage games played, and then all like managing pitch counts?
Mm-hmm.
How do we tackle this from the capacity side in order to prevent injury?
Yeah, so every sport has basically a force profile that we know certain joints or certain tissues are going to need more capacities, right? So we know in pitching, the elbow, the UCL area is going to need more density, right? Um, the knee in basketball, the Achilles, the ankle. So if we go about our training and part of the specificity of the training has a component of this connective tissue aspect, um, we can basically fortify those areas by creating a thicker UCL. Um, it doesn't just get thicker by doing, elbow muscle work or knee muscle work. We need to bias the connective tissue through very specific loading parameters, more like we've talked about in several other episodes, more through that isometric loading rather than, a movement. A movement is always going to bias the muscle over the connective tissue.
Yes. Okay, so kind of previously, kind of we or previously, as far as rehabbing injuries, we're kind of stuck in this kind of outdated model because the way usually injuries are treated is from a rehabilitation standpoint, it's really just kind of the idea is that you're just bringing tissue back to the capacity it was before. We're not actually improving it.
Yeah, so I mean, that's kind of this. Why would we expect any different, right? If they got hurt in the sport at which they're playing and we bring them back to that same capacity, why wouldn't we expect them to get injured again? Because we never actually bulletproofed or improved the tissue's capacity. We just put them right back into the same sport, the same activity, with the same tissue quality, roughly, right?
Yeah.
So it's not a surprise whenever someone has a calf strain and then down the road they now tear their Achilles because it's just a complication of the same problem.
Yeah. So we have this previous injury. We kind of bring it back to what they kind of deem as their previous level of capacity of the tissue. But in with typical rehabilitation, you kind of see a lot more movement based, like rehabilitation, and it doesn't seem to be specific enough to really strengthen connective tissue, which you need in order to prevent injury. So like whenever you rehab or whenever an injury happens, in order to kind of get you back in the game, essentially your body just lays down tissue fibrotically in every sort of direction, uh, and then you end up having what we have like adhesions or scar tissue.
Right.
So we don't get this now. We have essentially this connective tissue dysfunction that's just kind of lingering around. And now when we go to put force through that tissue, the muscle, uh, whatever that range of motion is, now we're not getting equal force distribution
Mm-hmm.
across the length. It's now going to be kind of specific to certain areas and essentially putting more force into certain areas of that tissue, uh, and causing it to be a little bit more susceptible to injury.
Right. So there's a concept that there's no empty space.
Hold on. So we got this whiteboard here. We kind of drew out a thing. We kind of walk you through a little bit of kind of what we're talking about.
Yeah, so there's a concept, basically, there's no empty space. So when an injury occurs and there's basically disruption of the tissue, right?
Yes.
And so we can kind of see that in our muscle example there. So there's directionality of the muscle fibers. And so if there's a strain to the muscle, we're then going to see connective tissue being laid down, like you said, in this haphazard way. But in a typical scenario, it's not going to be laid down in that fiber direction. It's just going to be laid down in whichever way it gets distributed. And so now if we put a force through that muscle, like where that green zone is, that is not going to be able to transmit the force the same way as the surrounding tissue. And then if we take this down to the Achilles example, and we can talk more about this here in a second, but there's a concept called stress shielding. And so where the kind of the black squiggly line is, that's basically, again, where the fiber disruption occurred previously. And so now that density is actually less than the surrounding tissue. And so the way that force transmits through tissue is it basically goes through the fibers that can transmit the force the best. And so it avoids putting stress through that particular area. And what we know about tendons require load to maintain their health. So if we are loading more in that green area and the force is being kind of curved around that disrupted area, that whole right side of the tendon is now atrophying to a certain extent. It's losing its ability to accept load. So then if we then kind of go back to our injury equation, if we then put a force through the Achilles that's higher than its capacity, because it's now actually losing capacity over time because the green zone is taking up all the force, that red area is eliminating its ability to accept force. And at some point, that tissue is going to yield even under what would consider like normal everyday movements because the capacity has lowered to that extent.
Well, I mean, yeah, you go back and look at, I mean, at least Tyrese Halliburton, I didn't see Dame's happen. I did see Tatum's happen. And if you look at the way they tore their Achilles is just kind of like this, they were just stepping back, that heel dropped and then pop with the Achilles.
Yeah, so it's not like they were in the middle of a really intense play, change of direction, typically like what we would see with like an ACL. The interesting thing, I'll let you say what you're going to say.
So. Yeah. So I know with Halliburton, because he had a previous injury, so essentially we had already a strain is a slight tear in the fibers anyways. So it's just a slightly less degree than like an actual, like a full-on tear.
Right.
So somewhere in his calf, back of the leg area, he had some sort of mild tear, and then when he went to go step back, essentially that calf Achilles got lengthened and it met its capacity and the tissue yielded and his calf just ruptured.
And so you kind of, again, by our example there, so kind of where those black zones are, that's kind of that tissue disruption. And the point is, like, the muscle doesn't have the ability to transmit the same amount of force. So then that decreased force production, then it all then gets transmitted to the tendon. And then, unfortunately, it yields.
Yeah. So we have this injured tissue. What we see kind of before in our standard kind of rehab practices, we basically just try to bring that tissue either slightly less than or to the capacity of the tissue it was before. Mm-hmm. And then we're kind of sent back on our way. But we still may have underlying scar tissue, connective tissue dysfunction in there, So we're just kind of leaving ourselves up. We're making allowing ourselves to be a little bit more vulnerable going forward into the future. So what we really should be doing is kind of like in these off seasons,
Mm-hmm.
really trying to build the capacity in order to really mitigate injuries.
Yeah, and I think, we've talked about this before, but and I know this is challenging in the professional setting just because their schedules are so hectic. But this is where the assessment really comes into play. Like we've talked about, um, if Halliburton had a strain, the athletic training staff, the medical staff, if they knew that there was already some disruption, a thorough assessment to know the extent at which the disruption is already, like, because we need to create a risk profile, right? I know it's game 7. I know there's a lot on the line, but it's like now he's gone the rest of next season, or at least a good
Yeah,
majority,
he's
right?
your franchise player. I'm not sure what the protocol is in this, but like if you're a basketball player, you're going to have certain you should have certain risk categories as far as hey, we have an injury in this part of the body. This is a big red flag. This is a hey, we should be more cautious. And now this one you can actually play through. In the case of having a calf or a quad, some sort of lower body where all that tissue, all that load is getting funneled,
Yeah.
we should have a high risk. I mean, if they were I would personally be putting them through an MRI and then backing it up as we talked about, kind of with a like an ultrasound to see if as we put that tissue through movement, we can see if there's like that more fraying of the fibers there.
Yeah, because unfortunately, even with some contrast MRI, we're not going to necessarily, and yes, there are some dynamic MRI, but to be able to see how that tissue responds under load, because sitting or laying on your back in the MRI tube isn't necessarily going to tell us how it's going to respond in a game situation or even in a training situation. So if under, say, ultrasound, and we start to load the calf, load the Achilles, if we start to see this fraying start to happen, it might not be fully torn. Um, that's just going to put us at a higher risk for especially that dynamic eccentric loading. Because there's a concept that I think we might have talked about previously, um, but it's called reversal strength. So whenever we go through a movement, say just a bicep curl, right? So if we go to kind of lift the weight, as we lift the weight, we're going through that concentric contraction, and then as we lower, there's basically a bit of a pause, and then we start to lower. So it's where the muscle transfers from like concentric to eccentric. There's kind of that transfer between. So in the case of these Achilles tears, they're going into this eccentric lengthening, but they're never responding with that concentric to kind of reverse the movement, right?
Yes.
So the eccentric moment just keeps happening until the tissue breaks. Um, so whether that's neurological fatigue, whether that's tissue fatigue, whether that's tissue capacity, tissue architecture, like there's a lot of reasons why that might be happening. But as we see, the only way that they're typically addressing this is just through rest. Just stop using it for a short amount of time.
Yeah, and it kind of makes me think you mentioned for like neurologic. So this idea of rest, it's essentially kind of you could maybe argue that it's actually uh, making injuries, increasing the likelihood of injuries because you're now allowing enough time for more like this neurological recovery, uh, and but they haven't you haven't nothing has happened to the actual tissue itself. The tissue is still compromised, and now that they're feeling a little bit fresher, they can go back to putting like full full force and a full level of effort into it, and that going into a compromised tissue is I mean, you're just asking for.
Well, yeah. So the highest level of athletics, I mean, basketball, football, doesn't matter. We know that their nervous systems are the best of the best. And so, like you just said, if they're giving their nervous system a break and then now it's able to recover, but the tissue is compromised, as soon as they go to put a force, it's going to be that pop, right? And so again, the equation that we're kind of referring to is kind of that load capacity. They're really not even addressing the capacity aspect to much. I mean, yes, the strength and conditioning team, they're trying to make the athletes stronger. They're trying to kind of work around the injury, but clearly we're not seeing an improvement, right?
Yeah, I mean,
Especially whenever we've seen the most Achilles tears in one season,
well,
right?
I would think, there's an argument to be said that you could say injuries are at an all-time high across sports, uh, and I think I would contribute that, and maybe you think differently, but like we're we're seeing sports just get the sport science and training gets so developed, but it's really all revolved around the muscular system. So we're seeing improvements in sport performance. The games are getting faster, uh, higher scores, more, just better overall performance. But that's because we've introduced, this training system that's based based around musculature. So we're getting increase in force production, but we're not addressing the issue of like stiffness, where it's what actually governs the muscles. So this our connective tissue is what our muscles actually grow out of. But if we're developing one system but not developing the other system, now your muscular system's at all-time high, but your connective tissue system's down here. And where does that injury happen? It happens down here at the connective tissue level. So we need to work on increasing the capacity of the tissue above the load requirements of what's happening in our sports in order to really truly prevent injury, uh, and just create long-term success.
Yeah, and if we go back to baseball, so pitching, UCL injuries, it's just one of those things that tissue has to take all the load in decelerating the arm, right? And so the velocity just keeps going up and up and up. And now we're seeing over 100 miles an hour with several people, right? Um, and so because velocity has become like the number one thing that all teams are looking for,
Yeah.
And we're not really seeing this connective tissue bias, because the connective tissue is how we absorb that force, right? Um, so because of that, it's really no wonder why we're seeing all this, injury and explosion of increased injury, because we're only working on the musculature and the nervous system's ability to create force, not the connective tissue's ability to absorb force.
Yeah. So trying to prevent injuries going forward. Yes, strength training definitely serves its purpose in strengthening musculature around the area. Will definitely help absorb some of the force, but unless we've gone through a screening process and assessed the tissue, assessed where we may have connective tissue dysfunctions,
Mm-hmm.
it can only do so much. So yeah, like we said before, we really need to kind of tackle this, really start looking at things from more of a connective tissue standpoint, which one is going to help prevent injuries, but then also increase performance as well. Because if we can create more stiffness, we can then keep developing the force producers, the muscles, and just keep the results going.
Yeah, and so we didn't really talk about this, but like the NBA specifically, like they kind of look at this acute to chronic workload, where they're basically kind of taking the risk profile based on the workload. So if we look at like that middle green zone,
Mm-hmm.
that's kind of the sweet spot where the risk is minimal. And then if we're outside of that, that's where we start to see an increased risk. So the interesting thing is the boom and bust makes sense, right? So if you do more than what you're prepared for, it makes sense that you would get injured. But this other side of the graph tends to be a little bit more nebulous in the fact that why would the injury risk actually go up whenever the workload actually decreases? And it's getting back to that point of the connective tissue needs load to maintain the health. And so if you almost neglect that aspect of it just by taking a break, and then you go back and put in those same forces that you're used to putting into it, it's actually susceptible to injury at what would be considered normal workloads. Like you don't even have to exceed normal capacities, because the ability to absorb force has even dropped further. So
Yeah.
kind of interesting way that, and that kind of comes from rugby and Australian rules football, but it's been applied across all sports at this point.
Yeah. So going forward, how do we go about, because I don't think we've released these episodes yet talking about uh, really how to train the connective tissue.
Mm-hmm.
But let's maybe just kind of give a brief overview as far as like progressively loading and
Mm-hmm.
just kind of building the capacity of the tissues.
Yeah, so I mean, we've talked about isometric loading. That's really where we start. So if we were to take the calf example or even the Achilles tendon example, we would want to find the zone where we start to feel kind of that stretch, if you will, because the goal is, well, let's kind of take a step back. So going back to this the tendon example.
Mm-hmm.
So if we put a quick force through the tendon, the force is basically going to skip over the disorganized zone. It's going to go through the that green where the green arrows are. But if we put a long duration isometric load into the tissue, what we're going to do is that green zone eventually is going to start to fatigue a little bit. And then we can actually start to shift the load into the disorganized area. So the goal is we put the tissue under a safe load at what the tissue can handle, but we need these long duration holds, typically over 30 seconds. 30 seconds is kind of the minimum.
Mm-hmm.
And so at that 30-second mark, that's where we start to see a little bit of what we call stress relaxation. So the stiffer zone is able to relax, and we're able to actually transmit into the disorganized zone. And so if we've got these disorganized fibers, if we're putting that tissue under load, the goal is over time that we get those fibers to start creating directionality again and in the fiber direction of the load. So that would be kind of the long-winded version of like, and so we would just have to figure out where along the movement path does that happen, and then we would just train it kind of along those parameters.
Yeah, and that would be kind of looking at that from a more like rehabilitation standpoint, as far as getting that tissues kind of essentially back to the capacity that it was, or actually now functioning properly the way it should. Now maybe you want to speak a little bit on is like now the next step, once we've gotten that, now how can we really develop that capacity to be greater than what our sport's going to demand?
Yeah, so we have to develop the architecture first, and that's kind of what we just talked about.
Mm-hmm.
And then we need to increase the load bearing capacity. So this would be where we traditionally see quote unquote plyometrics. And that kind of takes us to like this reactive strength. So the RSI, the reactive strength index, is typically what's used in basketball for one, but in a lot of other sports. And that's using basically a couple of different jump tests. And so they're basically looking at time and height. And so if we see a drop in height or an increase in time, the index actually drops. And if we see increase in height, decrease in time, the index increases. So that's kind of like the reactive strength measurement. And so reactive strength is kind of what we're talking about as far as like being able to build capacity. But the interesting thing is the reactive strength is not looking at the connective tissue part. They're really only looking at force production and the speed at which it can be produced. So we really have to then also add in this connective tissue component as well.
Yeah. Okay, so now once through plyometric training, I got also probably some eccentric loading as well.
Yeah, and plyometrics are what everyone really like knows, but there's a lot of like overspeed eccentric, like there's a lot of things like that I could say, but you're not going to be able to really put your mind to. So just know there are ways of specifically training that connective tissue load bearing capacity in a very specific way that's isolated to the zones that we're talking about. But it's not in what we would consider traditional training. It's going to be along the lines of
It's probably not going to have a named exercise.
exactly. And so that's the reason why whenever we see these injuries, like your first thought is, well, what exercise do I need to do to fix this? And it's like there might not be a named exercise that targets. Like if we see this in a hamstring curls aren't necessarily going like that's muscle, right? That's not necessarily going to bias the connective tissue. So we would need to set up an exercise that targets this in a different way. And again, it's difficult to explain without seeing it in action, right? So that might be a future episode.
Yeah. Generically, you're loading at length.
Correct.
You're loading going to length.
Yes.
And you're loading going to length with optimal velocity.
Correct. And so if we think of muscles are basically our speed profile. So that would be kind of like how we moder- moderate speed. And so if we train slow in the rehab setting, eventually we have to speed that up to game type situations, right? Otherwise, they're truly not going to be prepared. So the speed component is something that we definitely want to get to. We just don't want to do that. Like we wouldn't want to go into plyometrics too early. Otherwise, we're going to set them up for compromise and or injury again.
Yeah. Anything else? Missing anything?
No, I think we touched on the graphs. We've touched on the components of connective tissue. But yeah, like you said, the loading at length, loading to length. I think those are the key components where, again, it's not a named exercise. It's not a muscle-based exercise. So it's a little different than what people are traditionally used to seeing.
Yeah. Okay, I think with that, wrap this up. Let's stop counting minutes and start counting microns. Obsessing over load management and ignoring specific degradable scaffolding that holds athletes together isn't science, it's negligence.
That's right.
We need to kind of stop training the red stuff for show and kind of really go after the white stuff, which is really going to be there for our performance in sport. So yeah, thanks for joining, and come back next time.
We'll see you again soon.